Okay, let's go ahead and get started. So this week is the midterm week, so make sure you take the midterm exam. You can take it on Dropbox. You just click that link there. You get one attempt, 75 minutes. It's 20 questions. Make sure you take it alone. The questions are similar to the quiz questions, and I'll do a review today. And because it's a midterm week, I won't cover. Not planning to cover much new material. We also had quiz 4, which was due today, and I looked at the grades. They were great, but I'll very quickly review that. If you have any questions, let me know. So and by the way, the exam does not cover SystemVerilog. It just covers everything just up to the point where we did the Verilog lecture last week. So 2 operations you can perform on SystemVerilog are simulation, synthesis. Simulation tests the codes, synthesis deploys it on an Fpga or an ASIC design. ASIC being a custom chip. What's the problem with the SystemVerilog module below? Looks like there's 2 assigns that both assign to Z. Keep in mind that every assign and every always is a circuit, as well as any module that you instance to drive a module that you instance. So in this case, you have a module with 2 circuits in it, and both of those circuits are driving Z. And Verilog uses push-pull type drivers by default. Now there is a way that you can use a tri-state buffer in Verilog if you declare a logic as a try instead of as a logic. But everything we do in this class is just using the logic data type. Actually, well, I should point to this one, logic Z, and we're assigning Z is not a tri-stated signal, meaning that only one circuit should drive it at a time. Otherwise, you risk that signal being in conflict. So signal Z is potentially in conflict. I say potentially because if both statements set it to the same value, then it's technically okay. But there's a possibility that both circuits will try to set Z to different values, 1 to 0 and 1 to 1, which is a problem. Does SystemVerilog support structural or behavioral HDL? Both. How many possible values can be assigned to type logic? You would think 2, 0 and 1, right? But actually there's 4, because there's X and Z. Z is the high impedance tri-state value. X is like an undefined, unknown, or it's also used for signals that are in conflict. VHDL actually has 6. In VHDL, there's a U value that stands for undefined. It's used for memories that haven't been initialized. Or I should say it's used for memories that haven't been initialized. Oh, well, actually, so input and output, that's a good question. Input and output isn't a type in Verilog. It's like a modifier. It's used for defining inputs and outputs to modules. The basic type that we're using is logic. And I mentioned a few minutes ago there's another one called try. But we're just using logic in this course. Okay. And there's actually others even beyond logic and try. I think there's you can have one that's like floating point number. I think it's real, if I remember correctly. There's integer. There's some others, but we're just focusing on logic because logic is synthesizable. It can be synthesized, right? So when you talk about logic, what is logic meant to be? Well, that's meant to be a binary value, 0 or 1, right? So basically it's 0 or 1. But there's some additional values that it can take well, there's a Z potentially, which is high impedance. Now, the question there is, if you have it declared as a logic and not a try, can you assign Z? You still can. In fact, you'll notice if you use the simulator, which we're not actually going to do in this class, you'll do that in 611. This class is just an intro to SystemVerilog. I'm just giving you a quick and dirty introduction. In 611, we'll be actually simulating SystemVerilog in a simulator. And in the simulator, if you don't assign an input, like say you simulate a module like this, say you simulate this and you don't actually set anything for A, B, and C. Like no one's setting that, there's no stimulus, right? Those will actually get a value of Z, which means they're floating. They're not connected to, they're not being pulled down to ground, they're not being pulled up to VDD, they're just floating, right? They have no, they're not being explicitly set to a voltage. Does that make sense? So that's what Z is. Z is high, Z stands for, well, it stands for high impedance, although you would think if it stood for high impedance, it would be H, right, or something like, or HI. Z is a special letter that's denotes high impedance. Does that make sense? When you might say, well, what do you mean by high impedance? It means that there's a high impedance between that signal and power or ground. Power and ground, I should say, right? It's, in other words, because when you use a transistor to pull up or pull down a signal to power or ground to make it 1 or 0, you're providing a low impedance, right, to power or ground. High impedance means I'm not pulling it anywhere. It's just floating, right? If you measured its voltage, it would be indeterminate, right? So that's Z. And then there's an additional value, there's a fourth value you can assign to a logic signal called X, which is used for several things in Verilog. It's a don't care, it's a contention, it's an unknown. It's kind of like the other case, right? So if the simulator doesn't know what it is, it's X. Does that make sense? So it's 4-state logic. Instead of binary, there's actually 4 states, right? It's like a quaternary value, right? X is really just for simulation purposes, right? Whereas Z is a real concept. Z is something you could actually set it to in real hardware, because Z means don't pull it up, don't pull it down, just let it float, right? That's Z. And then 0 or 1, of course, is either ground or VDD, right? So there's 4 states. Now, one thing I want to mention is there's a very popular compiler called Verilator. You might come across this. Verilator is a way, it's a program that you can download on any Linux machine for free, and it will actually compile Verilog into an executable file. It's pretty cool. I mean, it's nice, right? In fact, I was going to demo it in this class, but it has one horrible weakness. It only supports it only supports 0 and 1 for logic signals. It doesn't support Z and X, which to me seems like that would break the Verilog standard, right? I mean, that shouldn't even be allowed, right? But yet they do it. Somehow they get away with it, and people still use Verilator. I don't like it. I don't like how there's only Verilator doesn't support the X and the Z. Yeah, exactly. Yeah, I don't see it. It's not a complete implementation of Verilog, at least in my view. There's probably some rationale behind that I'm just not familiar with.
VHDL actually has 9 values.
It was 9? Okay.
Looking at this Wikipedia article, I'm like,
I've used
this later.
So in VHDL, I've used dash, which is don't care. U is undefined, and then of course there's still a Z and an X and a 0 and a 1.
I also have W, L, and H for weak drive as unknown, logic 0, logic 1.
Okay, interesting.
So I guess that would be if you're working with like a mixed matched like push-pull design where some will naturally be a like weak drive logic 1.
Yeah.
To pull that part down. Or if you had a different one in the same hardware that defaults to logic 0, you have to pull it up.
Now that you mention it, SystemVerilog has a concept of weak 1 and strong 1 and weak 0 and strong 0.
If they a different value, they hide it, I bet. That's
yeah, but for the purpose of this class, we just deal in the 4 states for logic. Okay. But yeah, the point is that yeah, there's more than 2 values for logic, even though it's meant to represent a bit. That's the idea. Okay, consider the following SystemVerilog modules. There's a bottom and a top. Top instance is bottom. What is the value of A and Y within my thing? Okay, so my thing is what we're calling the bottom instance inside of top. So inside top, we have two internal signals, y and a. There's no inputs or outputs on top, but we do have two internal signals, y and a. We assign y to be a 1, and then y is used as the input to my thing, and a is the output of my thing. Okay, but inside of my thing, we're actually in the bottom module, because that's what my thing is. And so y is going to be the output. So we don't know what that is yet until we consider the input. The input is going to be whatever y is here. So y is 1, so the input is 1. And so then that's going to be complemented to become 0. So y is going to be 0 and a is going to be 1. Make sense? So a, y. A is 1, y is 0. 1 and 0, right? That should be 1 and 0. Yes, 1 and 0. How many bits are in the following constant number? 11. Just, it says 11 right there. 11 apostrophe b. To what is the value of b set in the SystemVerilog snippet below? So this is a bit manipulation. So we're going to take 2 copies of bit 1 on a. Bit 1 on a is what? Well, a is 4 total bits. They're labeled 3 down to 0. Right? 3 down to 0 to make 4 bits. The value there is 3 in decimal, which is 1, 1 in binary, right? So that means that bit 0 and 1 are both 1, right? And bit 3 and 2 are both 0, because it's 0, 0, 1, 1. So bit 1 is going to be a 1, so we're going to have 2 copies of 1, so that's going to be 1, 1 right there, right? The first 2 bits of b is 1, 1. And then the least significant bit of a, bit 0, is of course also 1. So it's going to be 1, 1, 1, right? But that's only 3 bits. And we say up here that b is declared as 4 bits, right? So if b is 1, 1, 1, and we want to put that in 4 bits, then we're going to have to pad it with zeros at the beginning, right? So it's 0, 1, 1, 1, right? So it should be 0, 1, 1, 1. Oh, that's not an option. Oh, wait a minute, did I do that wrong? A is 3. Bit 1 is 1, so it should be 1, 1.
The 2 is wrapping the 2 sets of 2 bits.
Oh, yes, sorry. Thank you. Thank you. Yes, excellent. Thank you. I missed that. You're right. The braces, see? The braces wraps around A, 1, and 0. Yes, thank you. So we're duplicating not just bit 1 on A, we're duplicating the pair. So it's going to be 1, 1, 1, 1, right? Yeah, we're going to take 1, 1 and duplicate that 2 times. Yes, thank you. 1, 1, 1, 1. Okay. How many bits comprise the signal A? 4, because it's 3 down to 0. To what value is A set in the SystemVerilog snippet below? Okay, this is. Let's see. Okay, so we have A is going to be the value of 2 shifted by 1 bit to the left, which is the same as multiplying by 2, right? Shifting 1 bit to the left is so 2 multiplied by 2 is 4. So this sub-expression is 4. Now, I'm assuming that the operator precedence will do the shift before it'll do the double equal. I think that's a safe bet. I have a table in the slides that show the precedence, but I'm assuming that's going to be the case. So 2 times 2 is 4, and we're checking to see if 4 equals 4, right? So 4 does equal 4. Now, the only thing that's a little tricky here, though, is this 4 is in 3 bits. What about, so the right-hand side of this equals equals operator is 3 bits. The left-hand side is going to be a value that's going to be 2 bits, then shifted to the left by 1 bit. So how many bits comprise the left sub-expression here?
2 on the left.
Well, good question.
Something out if the shift. So something is going off that left side,
See,
it's vanishing.
Either that, or it's going to add the bit. It's just going to expand this from 2 bits to 3 bits, right? It's either going to shift it off or it's going to add a bit, right? I don't know.
I think it would shift it off. I don't think Verilog does like.
It off. Yeah.
My intuition says
I
Verilog
don't
does
think
nothing
it
for
would
you.
concatenate it.
Yeah, that's interesting. I actually don't know.
And your order of operations was correct.
Don't know the answer to this. I mean, this is 4, right? 2 shifted by 1 bit to the left is 4, but the question is the bit width. So if it's true if they're both 4, right, and we can make that comparison, then the answer is going to be 1, right? Otherwise it's 0, right? Which, by the way, this whole thing is redundant because I think if you use double equals, it resolves to a single bit either way. So using the trinary to do this is redundant. I mean, you could have just not done the trinary and just had this sub-expression. I think it would have been equivalent. Okay, so what do we think? I'm going to say Verilog figures out that 4 equals 4. And
it might not even let you, the comparison between a 2-bit width and a 3-bit width,
yeah, it might generate an error, and that's an option. Okay, well, I'm not sure. I forget. Well, let's find out. It's 1. I think I tested this in the compiler, but that's, yeah, that's tough, actually. That's tough because it might, you're right, it might have generated an error because you might have been comparing 2 bits to 3 bits. Yeah, that's tricky. Okay. In the SystemVerilog code snippet below, to what value is signal A set? This is another bit manipulation. This one actually, this is pretty neat how you can do this. You can assign multiple values, but in this case, we're actually assigning values just from A, but in reverse order. So this is taking the octal value 10, which is 8, but it's encoded in 4 bits, which is good because 8 and 4 bits is 1000. So we're going to take 1000. That's a 4-bit octal value of 10, right? Octal 10 is decimal 8, right? And decimal 8 in binary is 1000. So we're going to take that and just reverse the bits. So if we reverse the bits of 1000, we should get 0001, right? Yeah, that's what it is. That's a good one. I like that question. Yep. Okay, that's it. Any questions? Okay, so let's, I want to run through the rest of lecture 3. I think we covered most of it. We talked about VHDL and Verilog. VHDL, as I mentioned, is a Department of Defense creation, and Verilog is an industry creation. Both came out at the same time. They're both the most commonly used HDLs, although there's some smaller ones that people use. Most notably, Chisel is the one most people are talking about these days. But by the way, if you ever hear about Chisel, Chisel came out of Berkeley. Chisel is a language that's actually an upstream language from Verilog. So when you write code in Chisel and you run it through their compiler, they still generate Verilog, right? So basically, Chisel is kind of a more abstract language. It doesn't replace Verilog. It actually generates, you're still using Verilog if you use Chisel, but Chisel is acting as a kind of as almost like a script that you're writing to generate Verilog, essentially is what it is. Now, BlueSpec, on the other hand, which came out of MIT, that one I believe is just a straight up HDL. It doesn't get converted to Verilog first, if I remember correctly. But those are just some examples of smaller ones. But VHDL and Verilog, or SystemVerilog as it's now known, are the 2 standards. And as I mentioned, I'm just introducing it in this class. I just want to teach you enough of it to write a simple module that we can put into Platform Designer to control the LEDs, so we don't have to use software for that. So I mentioned that there's a design hierarchy. The module is the heart of that, or the kind of the way that the foundation of the hierarchy is the module, because modules can be instanced in other modules. More abstract modules are at the top of the hierarchy. The less abstract ones are at the bottom. They're the leaves, and those ones tend to more be behavioral, right? Those ones have logic in them, whereas the ones up higher in the hierarchy are just instances of other modules. So what the point of that is that when you look at most Verilog code is just structural. It's just schematics that are written in code. In order to actually get to the behavior, you're going to be in the less abstract ones, and those ones will, have assign and always statements. Does that make sense? Oh, by the way, the problem is that this hierarchy is not obvious from looking at the code. Like if you look at code, it's just a set of files. You have no idea how they relate to one another. That's the part that really stinks about Verilog. Like if someone were to give you a set of Verilog files and say, here you go, figure out how this works, I mean, you have no idea how the hierarchy looks. You don't know which ones are more abstract, which ones are less, unless there's some kind of documentation that describes that. So that's one thing I don't like about Verilog, is that this structure is super important, but is not really obvious, by looking at the code in some cases. And then there's this notion of regularity too, by the way, which is where you're trying to design your modules for maximal reuse. So it's kind of like the same concept as writing a method, like in any programming language, right? You want to maximize the reusability of your modules. And you might say, well, that's obvious, but sometimes it's not. Like when you're writing the code, you may not know how to divide your code up or your design up into modules. It's not always obvious. You could write a really long module and have a whole CPU in one module, or you can write a whole bunch of small modules that collectively comprise the CPU. In 611, the other course I teach, I tend to design the whole CPU in like one big module. But other students in the class, they write lots of little modules. They like to divide it up, right? So, in one sense, it could be a question of your coding style. In the case of the CPU in 611, it's pretty simple. If you're working on a larger scale project, it's more important, I think, to make sure that you design the modules to be reusable. Okay, anyway, we talked about that. That's the syntax of a module. So this is a module that instances another module on the right, and you've got a module that just has behavioral code on the left. In this case, a behavioral module. The behavioral code is in a sign statement. Ultimately, the behavioral code is just Boolean logic, right, in memory. That's what it comes down to. Or you can mix them together, as I did in that one. This is an example of structural Verilog, and it's shown graphically. And it also shows how the same signal, the same physical wire, has different names depending on where you're looking at it, which module you're looking at it. So this N1 is the same as Y inside the AND gate, and it's the same as A inside the inverter, or N1, as I mentioned, in the NAND, the top module. And then this slide shows a simulation of that. Notice that I've got A, B, and C are being driven by some kind of unknown, entity, right, is driving A, B, and C. This would normally be done by a test bench. It would be another module that would do this, or a script. You could write a script to do this too. But somebody is going to be testing this module, so they're going to be changing the values of A, B, and C. Those are the inputs, and they're going to be looking at Y, which is the output. So you're changing the inputs, and you're looking at the output. That's the purpose of the waveform there. Okay, so we talked about the assign statement and how it can be synthesized in a number of ways. We talked about the conditional assignment and how the conditional assignment is very common in Verilog because it creates a multiplexer. This is the only way you can have conditional behavior outside of an always statement, because you can't put an if statement. So this is basically an if statement, right? If the select is 0, then I want to assign Y to be the first input D1, the first input D0, and otherwise I want to assign Y to D1, right? It's a multiplexer is the hardware version of an if statement. And so you have a lot of multiplexers. It's the way that you can establish data paths inside of a CPU, for instance. Hopefully you remember from 212 that there's a lot of multiplexers inside the CPU design, and the ternary operator is a natural way to express that in the code. We talked about internal signals. We talked about SystemVerilog syntax. Gave some examples. Talked about numbers and how you represent numbers. And then we got to the always statement. Now this one is, this always statement, it's also called a process. In VHDL, it's called a process. But even in Verilog, if you simulate it, it's listed as a process. I don't know where that term comes from, but that's essentially, it's a block of code that behaves atomically like a circuit, right? That's essentially what an always is. It's multiple lines of code, because an assign is one line of code, or it's one statement, and it's a circuit. If you want to combine multiple lines of code into one circuit, you have to create, at least behaviorally, if you want to create multiple behavioral lines of code into a circuit, that's an always statement. So the always statement has a sensitivity list, and then statements, which can be enclosed with begin and end. So this always statement is the same as saying assign y equals a or b or c. And if you have an always statement, or if you're you're coding in an always statement, you can use if statements, case statements, and loops. So in other words, always statements introduce constructs that are more familiar to someone who is used to programming in other high-level languages. You can't put an assign in an always statement. You can't put structure, and you can't put all other always statements. You can't nest always statements. That doesn't make, you can't, in fact, you can't, come to think of it, you can't nest modules. You can't have a module declared in another module. You can't have an always inside of another always, which is, I guess it makes sense. But those are the restrictions you work under in Verilog. So, as I mentioned too, this is an important point, but when you have an always, anything you assign in an always, and you can have multiple assignments. You could have multiple lines in an always block that assign signal. And you can even assign the same signal more than once. The only one that matters is the final time you assign it, the only one that actually takes effect. But anything you assign an always makes that always the owner of that signal, the driver, right? Unless you create a tri-state, unless you have a tri-state signal, which I have actually never done in an always. But generally speaking, anything you assign in an always is owned by that always. You don't want to assign the same signal outside of that always. So here's an example of two conflicts. In the first case, I assign y inside of an always, and then I assign y in an assign. These are both in this, assuming that these are both in the same module, right? Then y would be in conflict, potentially. In the second example, I assign y in an always, and then I assign y indirectly through this instance. I instance another module called my module, and I connect y to one of its output ports. So in this case, I'm driving y through my module. My module is setting y, and also this always is setting y. When I say setting, I mean driving, pushing it up, pulling it down. So in either case, you have a conflict there. And then always can also be used as sequential logic, or sequential logic meaning memory, meaning something, data that you're saving. And the way you do that is by having generally speaking, is by having a clock in the sensitivity list and nothing else, except maybe like a reset. Okay, so what's really happening here is there's nothing special about the clock. What's happening here is that I have an input D inside this always that's not in the sensitivity list. If you have any inputs at all that are treated like inputs in the always, like in other words, they're on the right-hand side of an assignment, or they're used in an if condition, right? Or they're used in a trinary condition. Anytime you use an input in an always that's not in the sensitivity list, that's automatic memory, because what that means is that the always has to capture the state of that signal and save it. Even though that signal may change, I'm going to hold on to the old value of the signal, right? So now the same thing happens, by the way, if you have an output in always that you don't assign. So say you have an if statement that causes something not to be assigned. That also creates memory. Although that's usually undesirable. That's usually, if that happens, it's usually a bug. I don't think anyone ever intends and deliberately has that style of coding, right? You guys with me? Okay, so the point is here is that you can create flip-flops and memories and latches with sequential, with always statements. Okay, so here's an example of a counter. Now, by the way, the reason I'm focusing on this, by the way, is because I'm not sure if this might be obvious, but the protocols that we studied at the beginning of the class, SPI and I2C, all of those are circuits that would be implemented in sequential logic, right? Because they all have like a sequence to them, right? You guys with me? Like SPI, right? The slave select goes down, and then I have to count 8 bits off, right? That is basically what's happening in something like this, where you have this counter that's counting up or down. And it's keeping track of a count called count. Right? Okay, so bus controllers, like an SPI, master or slave interface, or a JTAG interface, those are all built with always statements, essentially. Now you could say, wait a second though, you could bit bang it in software. You could write software. Software could do that too. It can, but it's kind of uncommon. They call that bit banging. If you ever see that term, bit banging. Bit banging is when you have a GPIO pin that can be directly controlled by software, and then you write a program in C or even like Python that manipulates that pin to implement a protocol, right? And we used to have a project in the first version of this course. We actually had a project where we did bit banged UART, where we had you write code on not a Raspberry, what is this called? Atmel 328, Arduino. You wrote Arduino code that would do UART with bit banging, right? Which was kind of cool though, because then we plugged it into the computers and you could actually see, you could do the bit banging and it would actually send characters on the screen of a Linux machine. I thought it was kind of neat, but it's not very practical because software, it would have to be a slow protocol for that to work, right? A low speed protocol, because otherwise it would be difficult for software to keep up with a protocol that requires cycle accuracy, right? Cycle, because in SPI, you have to, you have a cycle. You have the interfaces to an SPI have to keep up with the clock cycle, right? So it's difficult for software to guarantee that it can keep up. So bit banging is kind of rare. People do it, mostly hobbyists, but usually whenever you have one of these bus interfaces, it's done in hardware. Now, by the way, the same thing goes for PWM. So we are bit banging PWM in lab 2. That's the whole point of lab. That's what you guys are doing now in lab, right? You're doing a bit banged PWM, and then as you can imagine, in the next lab we're going to do PWM with Verilog, right? That's going to be lab 3. Make sense? No one does bit banged PWM either. I mean, we're doing it, but only to show the difference. Yeah, stepping stone. Yeah. Okay. Okay, that was an example question. I think we talked about that already, and then precedence. And just to confirm, yeah, I guess, yeah, shift does happen before equals equals. Yeah.
Typically, lecture reviewing a little bit more of the details of PWM. We covered it in other classes, but given like.
Yeah, we didn't. There's not much to say about it. One of the questions about PWM is what's this? Like you got the duty cycle. Yeah. But then you've got the period or the frequency, and it's like, what should the frequency be?
What the load needs, and the load varies, right?
Yeah, we don't. Well, yeah, you're right. Depends on the application. We don't really. I don't know. That's the reason, by the way, in case you're wondering, in lab 2, I asked you to be able to control that. So the question is in the lab. I don't know if you guys have thought about this or not, but when you do the PWM on the LEDs, you can make them dim, right? Which I think it's pretty neat.
Cool. It's an application of PWM.
So I think Apple was the first company I've ever saw that came out with, you would buy, they had I don't remember which one it was. One of the not ThinkPad, God, memory is shot. MacBooks, yeah, one of the MacBooks. You'd plug in the charger in and the LED light would sort of get brighter and dimmer. It would breathe, right? And that was the first time I had ever seen anything like that. Sorry. That was the first time I had ever seen anything like that. And it was really pretty, it was just an application of PWM, basically. That's all they did. But when you think about it, it's like, what's really happening there? Are you turning on and off the LED really fast? Or is the LED actually seeing an analog voltage? Like, so in other words, like LED...
Yeah, which one is it?
Like when you look at the boards, like the FPGA boards, you can see the LED getting brighter and dimmer, but is it just an optical illusion that it's getting dimmer because it's really just turning on and off really fast, faster than your eye can perceive it? But the duty cycle determines how long it's on versus how long it's off. Like, which is it? Or is it really getting dim? I think the answer to that, it depends on the PWM frequency. And that's the reason why you guys can control that in your code. If the frequency is high enough, I think that the capacitors, I think the LEDs have a capacitance. And I think that capacitance will act as a low-pass filter, but only to a certain, only up to a certain speed. So if you have the PWM period or frequency, or whatever we called it, if that's low enough, it'll still work. But you're going to be getting a flickering. Like you'll see, I don't know if you'll see it, but the LEDs will be flickering. Whereas if it's fast enough, I think the LED's capacitance will smooth that out, right? That's the question. I don't know the answer because I don't have a model. I don't have a model of the LEDs on the
I would
board.
tell on the fly, by using an Android phone, you can take the video app and you can adjust how many FPS it's streaming at. And if it's too high enough, if it's too low in FPS, you'll be able to see the modulation of it.
Yeah, that's something we
You
could
get
try.
some really weird results in like 313 if you were pushing a video stream at like something like 30 FPS, and then you go and look at the 30 FPS through a camera. Sometimes if you misalign it, your screen will look blank through the camera, but smooth IRL.
Yeah,
You can
when you're
tell that
looking.
real quick if you wanted to next time you were in the lab.
Yeah, we could try that. In fact, that's something that I was hoping to do during the demos. Basically,
Yep.
that's when I
Camera, break it.
when I designed the lab last. I don't think we ever tried it, but that was kind of the idea.
That's something I found goofing off.
Okay, so anyway, but that's all. The answer to your question, that's all there is. A PWM is now there's pulse width and there's pulse phase modulation. There's different ways that you can modulate. PWM is only one of several.
That's the point where I say I'm not an electrical engineer.
Yeah. We just use PWM because why? Because PWM is for power electronics, which is electrical engineering, but it's the digital part of power electronics. Like power electronics have to be controlled by a computer, ultimately, like a controller. So PWM is what controls those, as well as motors. And there's a lot of variety of motors out there, but like even big motors, like you have like in an electric car, are ultimately controlled through PWM, as far as I know. So a lot of this cyber physical system stuff is PWM centric, and that's the reason why we cover it in this class. Make sense? That's the whole idea, is that we're trying to cover this physical aspect to the embedded.
Most computer engineers, we don't need to take the power systems is actually like a 500 level class.
Yeah.
We need the various kinds of PWMs and their scales. So you're not going to give us a problem that says design a P.
No. But what we're going to design the Verilog that generates it though in Lab 3. Yeah. But it's just a counter essentially is really what it is. Okay, so we talked about bit manipulation. Going to skip ahead a bit here.
Sorry.
Oh no, it's no problem. I just want to take about let's see, 35. Yeah, about half an hour for the review. Okay, so there's an example of an always here that drives multiple signals. It drives Y1 through Y5 all in one always block. So this always block is a circuit. It's going to kind of own all 5 of those signals. Notice it says always COM. That's a Verilog, SystemVerilog thing that says always COM means that anything that's treated as input is going to be in the sensitivity list by default. And if I have any code in here that implies memory, then the compiler will tell you that. It'll give you a warning. So this protects you. This basically, by saying always COM, this is telling the compiler that this is supposed to be combinational logic, meaning that there should be no memory implied. So if you had an if statement in here that said, if y1 equals 1, then y2 equals that, and then you didn't have any further assignment of y2, that y2 would create memory, right? It would create a latch, and the always COM would cause the compiler to give you an error for that. But that's optional. You don't have to use that syntax. Okay, and this is the final. Yeah, this is the final thing. Now this can get a little confusing. So in and always, there's 2 ways you can assign a signal. You can use the less than equal or the equal. The less than equal is a non-blocking assignment statement. The equal is a blocking assignment statement. What is the difference? The difference is that inside the always, if you use a non-blocking, then the assignment does not take effect, it is not seen by lines below that in the always. So in other words, all the outputs are assigned at various points in the always block, but it doesn't take effect until the end of the always block, right? Whereas with a blocking statement, if I set n1 and then I later use n1 in the same always, the code will be compiled as if I'm seeing the updated n1, right? Which in the case of hardware will cause, for example, this one, these two are the same, the only difference is the assignment statement, but in this case, this is going to create a shift register, 2 flip-flops connected in series. And this one just basically collapse down into 1 flip-flop, because if I say N1 gets D and then Q gets N1, this is basically just creating 1 flip-flop because N1 becomes equivalent to D, right? So basically what's happening here, because this is blocking, the N1 in the next line of code is just essentially being substituted for D. So what I really have in here is Q gets D, right? Whereas over here I have 2 lines that each of which create a flip-flop. So N1 will get assigned, but I'm still seeing the old N1 in here. And so this will end up taking basically 2 cycles for me to get the D value out through Q. It'll take 1 cycle to go to N1 and then a second cycle to go from N1 to Q. Now, why is that important? It's not for this class. All you have to know is if you write sequential logic, clock logic, you should use less than equal, and if you do combinational logic, you should just be equal. You guys with me? And by the way, I generally don't do combinational logic in an always, unless it's a special case, like a really big if-then-else, like in the control unit in 611. I usually use an assign for combinational logic. I only use always for sequential logic. You guys with me? In other words, I only use the always for memory. I generally don't never write code like that. I mean, you know, well, I shouldn't say that because that is actually clock logic the way it's written there. But I don't write code with an always that implements non-memory if I can avoid it. Okay. Okay, and then there's something else that you should know about. This is not a big deal, but there's also this notion of parameters, which are ways to write a module where it's a template. So any of you guys that are familiar with templates in C++, this is essentially what that is that a template in C++ is a way to have a class be customized in a certain way for a particular case. Like you can create a class in C++ that's like a linked list, right? But then you can customize it to define what sort of object you want to be able to put in that linked list, right? It's the same idea here with Verilog, but usually they're used for widths, most commonly, right? Or memory sizes or something like scale. It's a way to scale up a module. So like, you know, you could say, well, I want an 8-bit multiplier. Well, what if I want a 16-bit multiplier? You're going to write a whole new module? No, I just use a parameter, and then I can just set the width. I can have one parameter that'll let me generate an 8-bit multiplier or a 16-bit multiplier, right? Or if I have a cache, like say I create a CPU cache, I can just set the size of the cache, right? So I could just specify that. And the compiler will take care of basically creating a custom version of this module for the parameters that you set. So this is a compile time thing, just like it is in C++ with templates. So you can set these. Now the syntax here is bizarre. The syntax, this kills me. Okay, so check this out. When you define the parameters, when you declare the module, you say module and then the name of the module and then hash mark or whatever that is, £, right? And then open parenthesis, and you list your parameters using the full spelled out word parameter before each one. And then close parenthesis, and then another left parenthesis with your IOs. Okay? So basically, you put the parameters in between the module name and the IOs, right? Okay, that sounds straightforward, except the problem is that when you then use that module, it changes. Now, when you use it, you put the module name, then the parameters, then the name of the instance, and then the IOs. You see the inconsistency here? Like here, you have module, adder, parameters, IOs, right? That's when you declare the module. But when you use the module, it's module name, parameters, then you insert the module name in here, and then the IOs, right? I always have to look this up because I always forget this. So you basically, you can set default values here. And then when you set the values, if you don't want to use the defaults, you can set them the same way you set the IOs, right? So dot module name value, right? Makes sense? Now you might say, what is the data type there? In with, out with? What, it says parameter, but is it like a logic, or what is it? Integer? Unclear. I think normally by default they're integers. But remember, this is not, these are just parameters that are basically macros. They're being substituted into the code. These don't represent like bits, like signals, right? So that's why they can be integers, right? Integer is kind of it's kind of nondescript, right? You guys with me? So I'm not saying how many bits the in with is, because it doesn't matter, because it's really just a macro that's going to be plugged in. Make sense? Okay, and then last thing here that we want to cover is the generate statement. And this is another way to kind of create a template. It's kind of like a parameter, but the idea here is that we want to be able to write a code that will stamp out multiple chunks of logic in an array. So this is useful for like if you want to create like a multi-core CPU, or you want to create you want to have something that you can create copies of. Now in this class, the reason you might say that looks kind of advanced for just introducing, it is, but in lab 3, we're going to use this to create one PWM generator for each of the 26 LEDs. That's the reason I'm showing you this, right? This is where this is going. So, because you're going to write logic that does PWM, but you want to have a separate independent PWM generator for each light, right? You don't want them all, like in lab 2, you guys are going to do, they're all going to be synced, right? The lights get brighter, dimmer, brighter, dimmer, brighter, dimmer. But in lab 3, we're introducing this thing where we want them to all be independent. They should all have independent PWM values. So in order to make that work in Verilog, you would then just generate a PWM module for each one of the 26 lights. Now the syntax here again is kind of weird. I always have to look this up. But inside a module, not inside an always, but just in a module, you say genvar I, doesn't have to be I, but that's usually the variable I. And then you say generate, and then use a for loop. For I equals 0, I less than n. What's n? N's a parameter. I equals I plus 1. I plus plus doesn't work here for some reason. Don't know why. They don't allow that. And then begin, and then colon, and then the name of the generation statement, gen name. Now, why do you need that? The reason you need that is because when you simulate this, it's going to have to create instances that it's creating. And this is the prefix it's going to use, right? So if you put PWM, this is going to cause it to create PWM0, PWM1, PWM2, and so forth, right? That's what it'll be called inside the simulator. Now, outside the simulator, it doesn't matter because in real life, the names are irrelevant, right? The names of modules are only there for simulation. Yeah, for human, like for debugging, right? For human interpretation. Because when this goes into hardware, it just gets collapsed into a big mass of wires, right, essentially. Okay.
I have a question. This generator code is looking less like hardware description language and more like programming language that generates more HDL.
Yeah,
Is this
basically it, yeah.
Is actually doing like a tickle script inside the simulator, or
No, it's generated internally in the compiler, but yeah, it is very similar to like what a tickle script would do, because you don't need a generate statement. You could just, as a programmer, you can copy and paste. But the problem with that is you would have to copy and paste it a fixed number of times. It would be difficult to change n.
it
See,
would be.
the nice thing about this is n is adjustable.
Name everything correctly.
Yeah, but it's now the question is, well, wait a minute. If you're just copying and pasting the code inside the generate, what differentiates one instance from the next? Like how do you keep them separate? You do it through I, okay? And usually it's I is used inside the bits, the bit width calculation. So the important thing inside here is that we're creating an adder. Oh, this is actually creating a ripple carry adder actually. Yeah, so I'm creating a ripple carry adder in here. I forgot about that, right? This is creating an arrayed adder, right? Carry adder. But notice that I've got this calculation. So I'm creating an adder called, well, it's called my adder, but the name of it's actually going to be called gen name 0, gen name 1, right? But so the name, like I said, the naming is automatically generated. But my adder is the thing I'm going to be stamping out, right? And when I stamp it out, I'm going to connect A to a slice of big A. Big A is a signal, right? Yeah, see, big A is 32 bits. So I'm going to slice out a portion, and this portion I'm going to slice out is going to be 8 times I plus 7 down to 8 times I. So what's happening is that the adder is an 8-bit adder, and I want to create a 32-bit adder by putting 4 copies of the adder in there, right? So I'm going to take 8 bits out of A and 8 bits out of, well, big A. I want to take 8 bits out of big A and 8 bits out of big B and 8 bits out of S and connect them to each of the 4 adders. Does it make sense? Yeah, so it's just 8 times I plus 7 down to 8 times I. That's the, so that'll end up being 7 down to 0, and then 15 down to 8, and then 23 down to 16, and then 31 down to 24, right? Everything's just multiples of 8. You guys with me? Now, is there any other way you can differentiate these? Yeah, you can actually. Because you can also, well, actually I shouldn't say that, because I is the main way you differentiate code, right? It's just through I. I don't know of any other way to do it. But what I was going to say is you can also put an always statement in here. You don't have to put, this is not an always, this is just instancing an adder. This is structural. But you can put behavioral code in here too. You can stamp out anything you want, right? But in this case, we're just stamping out adders. Okay. Okay, and then we talk about FPGAs. Okay, I'll talk about this. I'll just give you a little preview for this. So I mentioned earlier that we're not going to use the simulator in this class. So you might be wondering, how do we test the code? We're going to use in FPGA testing. So we're going to put the Verilog on the FPGA, and we're going to test it on the FPGA. And you can do that through 2 tools, the in-system sources and probes editor and something called Signal Tap. The Signal Tap. Signal Tap's a logic analyzer, of a JTAG-based logic analyzer. It's really cool. You can monitor signals in there and just watch the signals in the FPGA. So we're going to learn those because I don't have time to cover them in 6.11, and it's something I want you to know in 6.11 so you can use it as a tool in 6.11. So we're gonna cover these. We're gonna cover this in this class and the simulator in 6.11. Does that make sense? And if you've already taken 6.11, then you won't.
No idea, but
Yeah.
looks useful. Looks extremely useful.
Okay, so with that, I'm going to switch over and let's run through a quick review for the exam. I just want to make sure everyone's. I think you guys are, I get the sense that everyone's pretty comfortable with this material, the SPI and I2C. The quiz scores were really high. So we talked about this notion of address ranges, I/O ranges. Make sure you're comfortable with this. There'll be a few questions on at least at least one, I think 2 questions about this on the exam. So address ranges are just basically ranges of addresses that you can use from the software to communicate with hardware. This is how all modern, hardware machines have, do hardware-software communication. So this is really important. You'll see this. This is comes up a lot whenever you do bare metal programming. And then we talked about bit twiddling, where you can set specific bits in values, basically just through shifting and bitwise ands and or.
Your lecture 3 slide.
This is no, this is in lecture 1 still.
Oh.
Yeah, I'm just going over lecture 1. So yeah, this is a way to set bits on, set bits off, single bits or even ranges of bits. Make sure you're comfortable with that. Yeah, as long as you understand like how shifting works, because, and by the way, shifting is something that's not really covered in programming classes. We do talk about it in 212, because we talk about the shift instructions, but you never really use it for anything. So this is finally an opportunity for us to use shift instructions. And basically the idea is that it's needed whenever you need to make changes inside of a word instead of a value. Okay. Okay, so for that, there's a few different ways to do it. So for 1 bit, I start out with, hold on, that's not it. That's not it either. Wait, let me go back. No, that was the first one. Yeah, oh, sorry. Yeah, here it is. So for 1 bit, I start out with a temporary value that I set to 1, right? And it puts 1 bit on the right-hand side. That's because I want to manipulate 1 bit. If I wanted to manipulate more than 1 bit, I would not just put a 1 there. I would put like 3 ones, for instance, if I wanted to manipulate 3 bits, right? But the idea is that I'm putting a 1 in here because this is my tool. Having a 1 in this temporary register is my tool for manipulating 1 bit in another value, right? Now I start with 1 and then I shift that, in this case over here, to move it out of that position. But the key to answer your question, if I'm manipulating 1 bit, I'm going to set a temporary value to 1, right? Just 1. That puts a 1 bit in. Now if I'm doing more than 1 bit, I think I have an example of that somewhere. Yeah, here we go. I want to isolate bits 5 down to 3. So how do I do that? Well, in this case, I think the first thing I do is get those bits to the right-hand side. Yeah. So in this case, I'm going to get those bits to the right-hand side, right? So I'm going to take that value and shift it 3 bits to the right. Why? Because 3 is the lower end of the range of bits I want. 5 down to 3. So I'm going to get rid of I'm going to shift 3 bits. Why? Because if you shift 3 bits, you're effectively subtracting 3 from both these numbers. So 5 down to 3 will become 2 down to 0, right? And that's what I want, because I want to get those to be right justified here, right? So I shift it. But then, now, obviously if I shift it, I'm going to have 3 zeros up here that are shifted in. But I still have garbage bits in between the bits I shifted in and the bits I want, right? I still have these 2 garbage bits I got to get rid of, right? The 0 and 1. So to get rid of those, I have to mask off. And this is where the multi-bit thing comes into it. So I need a temporary value, right? But instead of setting 1, right, because there's 3 bits, right? I want to do multi-bit. So instead of putting a 1 in there, I'm going to put 7. Why? Because 7 is 111, right? Now you might say, wait a second, you just can't put a hard-coded 7. That's a magic number. Charles would be furious. As my old student, Charles, he didn't like magic numbers. He liked there to be the ability to put a parameter in, essentially, instead of putting that magic number 7. So the way you get around that is you say, I have the code down here. 1 shifted by 3 bits to the left, right? Subtract 1. That gives me the 7, right? And that way, I don't need a magic number because that 3 can be a variable then. So basically, you take a number, you take a 1 and you shift it left by the number of bits. It can be anything, right? It can be like, say, 8, right? So I could take a 1 and shift it by 8 bits to the left. That gives me 256. And then I subtract 1 and it gives me 255. And 255 just happens to be 8 1 bits. Make sense? So multiple bits is, if you want to set n bits on in a register, you want to turn on n bits that are aligned on the right. You take a 1, shift left by the number of bits you want to turn on, and subtract 1. That's the way you do it right there.
Let me say that if you want to shift it 4 instead of 3, that would be a value you will shift 4 and 0, that's 16.
Right, that's right. 16 minus 1 is 15. That's 1111. That's 4 1 bits. So that'll get you what you want. Yeah, that'll give you the 4 1 bits. Yep. Okay, so then what do I use that for? Well, in this case, I'm just using it to mask. Because if I AND with 111, it's going to 0 everything except for the 3 bits on the right, where that 111 is. So hopefully I answered the question. So that's the difference between single bit versus multi-bit. It all has to do with that temporary register that you're going to use as a tool. So I have a summary of ops there for bit manipulation. And by the way, I didn't cover this in class. It is in the notes in the textbook, though, that I'm writing. If you looked, I don't know if you guys looked at these textbook chapters. There is another way to do this in C. There's something called bit fields. So in C, you can actually define a structure, and you can specify the number of bits of each of the fields of the structure. I only learned about this a few years ago. I was pretty surprised to find out this is pretty powerful. So you can say struct, and then I can have these fields. Now the tricky part here is they're ordered from, like this first field is 3 bits, 3 bits, 2 bits, but they're ordered from least significant to most significant. So if this first field is 3, that means it's going to be bits 2 down to 0, and this one's going to be bits 5 down to 3. 5, 4, 3. Yeah, right. And then you can also then, if you create a union between that and a regular raw value, right? Then if you put a raw value inside that raw value, then you can use these fields to extract the bit fields. Now you might say, well, wait a second, like, okay, you can do that in C, but then how does the C compiler actually generate the code that does the extraction? It does it the way that I just got done describing, I think. It uses shift instructions, right? But this is a way to get the compiler to do the work for you, basically. The compiler will figure out all the shifting stuff, right? So this is kind of another option if you want to write C code and you want to access bit fields, right, within a value. But the shifting approach works too. And like I said, that's how the compiler is going to do it anyway. At least I believe. Okay, so we talked about loads and stores, to how to generate load and store instructions with dereferencing in C. So if you dereference, which is the star, if you do it on the right-hand side, that's a load. If you do it on the left-hand side, it's a store. Right? This is the way that you do a load or store. Now you have to be careful with that, though. And normally, if you're doing programmed I/O, you're probably going to want to use an intrinsic to make sure that the proper load and store. This is why we use this in Altera, because if you don't do this in Altera and you just do this approach, you might get caught by the cache. The cache might cache you're going to set the LED to turn the LED on, but instead of going to the LED, it just gets captured in the cache, right? So by using this intrinsic, it causes the compiler to generate the correct instruction to avoid that problem. In the case of Altera, it generates a store I/O or a load I/O. Same instruction. It's just that the load I/O and store I/O bypass the cache. That's the only difference. They're just loads and stores. Nothing special about them aside from avoidance of the cache. Okay, then I had some questions, some example questions. Okay, and then pulse width modulation. We talked about this already, but that's basically I think I just have one slide on it. Yeah, there's not much to say about PWM. It's a basically just, it's like a clock. It's like a clock signal, except the duties, like in a clock signal, usually the duty cycle is 50%. You know, it's half up, half down. Half the time it's high, half the time it's low. PWM allows you to modify or use whatever duty cycle you want. In other words, that's the percentage of time it's high versus low. But the period is consistent, right? So generally speaking, the period of any PWM signal is constant. In PWM. There might be another modulation scheme where you change the period. But in this case, you leave the period alone, you just change the duty cycle. And the duty cycle could change over time, which is what we're doing with the PWMs. Right? All right. Interrupts, we talked about interrupts. There's a few questions on the exam about interrupts. So the interrupts is basically a wire that gets the CPU's attention. The problem is, how does it do it? There's different ways for that to work. There's different mechanisms. Not all interrupts are the same. An interrupt is a very generic term that just says, I have a wire that gets the CPU's attention, but how does it actually do it? Well, one way to do it is to be a level-sensitive interrupt where it's just the CPU is triggered by the level of the interrupt, right? And another way to do it is to have it triggered by the edge of an interrupt, right? The problem with both of these approaches is that it's only one-way communication. So the peripheral doesn't know if the CPU is process the interrupt service. I'm sorry, the interrupt doesn't know if the CPU has recognized the interrupt and started servicing it. That's really bad. So who would do that? Well, Arduino does that. That's why we have it in there, because we used to teach it on Arduino, right? The Neos doesn't do it that way. Neos has an acknowledge, right? But just to let you know that this is why the way that Atmel does it is bad, is that there's no acknowledgement. So like the peripheral doesn't know how long to hold that high, or it doesn't know if the CPU acknowledged it or if it finished servicing it. So for that reason, you should have an acknowledgement, some kind of feedback signal, right, to the peripheral. And that way, and this is, when you have that, that's really nice, because that way the acknowledgement tells the peripheral when the CPU begins acknowledging the interrupt, begins the service. So that allows the peripheral to know when to drop, right? So if it's an edge sensitive, I go up and I hold it until I get the acknowledgement back, in which case I can drop. And then the peripheral knows how long it takes the CPU to service it by waiting for it to drop its acknowledge, right? So that way the peripheral knows not to issue another interrupt until the acknowledgement goes low, right? So the acknowledgement is going to be high for as long as the CPU is processing the interrupt, right? That's nice. That's real. I love that. I think that's a nice way to do it. Okay, then peripherals, SPI. Make sure you know about the CPUL and CFA. You might say, what's the big deal with that? Why are you emphasizing that? Well, it turns out that if you use SPI, you have to be aware of that. If you want to do any SPI, it doesn't matter if you're doing a slave or a master or just buying two components off the shelf and wiring them together. You have to know what that is, because that is important, because otherwise it's not going to work, right? Even though it's a subtle difference. CPUL is, defines what the clock is at idle, and thus what the first edge is. CFA is the one that's a little bit more confusing, but CFA is, if CFA is 0, the data gets a head start on the clock, which means you can use the first clock edge to sample it. Whereas if CFA is 1, then the data and the clock change at the same time, and you have to go second clock edge. So CFA 0 is first clock edge, CFA 1 second clock edge. That's if you can remember that. Yeah, that's really all there is to it. It's just a matter of, it's important, by the way, because SPI is fast. I mean, it's not like PCI or USB Gen 2 fast, but it's fast. It'll do megahertz, megabits per second. I think you can probably drive an SPI channel up, in some cases, to hundreds of megabits per second. It's a fast channel. And so it's very important to know when to sample because it's so fast, and because there's so much capacitance on that, because it's a long wire usually, it's an off-chip wire, you have to make sure that when you sample that data, you have to have the data stable. Otherwise you get that metastability, and the metastability will happen a lot more often if you have a fast channel like SPI. With UART, it's so slow, it's like, it doesn't matter. If you get an error, you get an error. Plus you got parity in there, right? Whereas there's no parity here either, no error checking, no error correction here. So it's very important to avoid metastability, that you know exactly, that you're careful to grab the data at the right time. That's the reason why this is so important, just so you know, that's the rationale. That's what makes, that's the secret sauce of SPI.
Something else that you never mentioned, but my friend showed me quite recently, is he's working with a device that uses Pi. Because the clock periods and like the actual height of the clock can be like a little bit garbage too. You show me like a real device and the actual string, and like sometimes the clock, because it just looks for the edge, would like sometimes only go a little bit high, and sometimes the clock would go really high.
Oh yeah, because you got losses. Yeah.
It doesn't matter how high it is as long as it finds the edge. And I was like,
yeah,
this stream looks horrible versus like these nice textbook ones. But
yeah. When I was actually my dissertation was, I looked at a lot of those eye diagrams, which is where you take bits of a channel and you keep superimposing it, like on an oscilloscope, and you can see like, the clock edges are really soft. And not only that, but they also have jitter in them too. They're moving around. So what you end up with is an eye diagram. You have this,
exactly what you're talking
and
about.
the eye closes the more jitter you have. Yeah, so that's a good point. Yeah, it's all about signal integrity. That's the whole reason for this. Now, I2C, on the other hand, uses a totally different approach, and I don't actually know. I don't actually know how the circuit looks for I2C for doing this level sensitive stuff. So as I mentioned, I2C is, first of all, it's a open drain, and it's level sensitive. The clock is level sensitive. I mean, the only thing I can imagine for this is they use a latch instead of a flip-flop for I2C. They must use a latch for the data, a latch circuit. I don't know how else it would work. Now you might say, what's the advantage? I mean, I thought latches are always inferior to flip-flops. Well, I mean, in this case, I think latches are good because you guarantee that the data is stable while the clock is high, and that's the reason why people don't like latches. Have a bad reputation because it's tough to make that guarantee that nothing will change when the clock is enabled, right? But in this case, SPI is designed specifically to keep the data stable when the clock is high. So I think they basically just use latches. And again, latches are just like flip-flops, but they're level sensitive. When the clock is high, it opens the gate and the data comes in, clock goes low and it locks it off, right? It's like a lock, like a river lock, the gates go open and they close. So that's the idea with I2C. Now it has that weird start and stop condition though, where the data actually does change when the clock is high. But that's only the start and the stop. And the other thing you should keep in mind about I2C is it's an 8-bit, it's usually an 8-bit per word, but there's 9 bits in the first and second half because that acknowledgement adds a 9th bit. So the total number of bits here is 18 in this case. There's 9 of the header, 9 for the data, right? So I think you should be okay as long as you understand that. It's level sensitive, there's a start and stop, and it's 9 bits and 9 bits. And then, of course, we talked about JTAG. Make sure you understand JTAG. I talked about this state machine. So basically, this state machine is a set of, I forget how many there are here, 1, 2, 3, 4, 5, 6, 7, 14 plus 2 is 16 states. So there's 16 states, and the master is putting the slaves into one of these states based on a sequence of data coming in from TMS. So TMS gives a sequence of bits, and through that sequence, it can program the whatever's on the JTAG chain to go into whatever state it wants, right? So that's basically it. It's not that complicated. It's just a lot different from SPI and I2C. It's a very different, takes a different approach to control. And then of course there's TDI and TDO, which are the input and output. It's like MOSI and MISO. And that's JTAG. We're going to use JTAG is nice because it's the way that we can debug the FPGAs. We're going to use, that's how Signal Tap works, that we're going to use later. It goes over JTAG. It's also how the console works and how we program the FPGAs. All that stuff runs over JTAG. Now, not from the Linux machine. From the Linux machine, it's actually going over USB. But once it gets into the FPGA, it goes into the USB blaster, and then from the USB blaster, it becomes JTAG, right? So you're going to use JTAG, but if you look at the cable, it's not a JTAG cable. We use the USB cable. Okay, that's it. That's all I got. Any questions about that? About the review? Okay, make sure you don't forget to take the exam by Friday. And oh yes, the lab 2 is also due on Monday, but we won't meet on Monday because it's spring break next week. So just finish lab 2 this week, ideally, and then we'll just demo it the week after spring break. Okay, so. And then once we get back from spring break, I'll introduce the next lab, and then we'll get away from this hardware stuff, and we'll start talking about control theory and real-time systems. We'll be back into more abstract stuff. Thank you.